We'll now continue section 6.4 and continue our discussion on graphing the trigonometric functions. In this section, we will look at graphing the cosecant, the secant, and the cotangent functions. So let's begin with the cosecant function. The graph of the cosecant function is based very closely on the graph of the sine function. So I have the graph of the sine function from our last presentation. And so let's look at this and see if we can then draw the cosecant function. Remember that sine and cosecant are reciprocals of one another. So the first thing that I'm going to do is I'm going to note that on my cosecant graph, this graph will have asymptotes, similar to what we saw on the tangent graph. So my first question is, where are those asymptotes going to occur? And so in terms of my identities, I know that the cosecant function is the reciprocal of the sine function. So I know that cosecant is equal to 1 divided by sine. Again, remember that if you have a 0 in the denominator of the fraction, you're going to have an asymptote on the graph. So the real question is, where does sine equal 0? On those points where sine equals 0, we're going to have an asymptote. So I can look at my graph and I can tell you that I will have an asymptote at pi, because that's one place where the sine function is equal to 0. I will also have an asymptote at 2 pi. Again, that's another place where the function is equal to 0. And I will have one at 0, because that's another place where the sine function is equal to 0. So we have asymptotes at every other value, even multiples of pi. So we'll have one at pi, or not even multiples, but just multiples of pi. We'll have one at pi, one at 2 pi, one at 3 pi, one at 4 pi, and so forth, following that pattern. Now, the actual cosecant graph, remember, is a reciprocal of the sine. So let's look at this in terms of these individual parabolas on the graph. So we have, for the sine function, we have this parabola that opens down. So if we're moving to a cosecant, which is a reciprocal, what that's going to do is it's going to take this parabola that opens down on the sine function and it's going to flip it up. And so the blue graph is going to be the graph of the cosecant. Now the sine and the cosecant will share this point at 1. But otherwise, they will be the flip of one another because they are reciprocals. Similarly, if we look at this parabola on the sine function and we think about the reciprocal being the cosecant, we would expect that parabola to flip down. Again, it's going to share that point at -1, but it's going to mirror that parabola that we had with the sine. So what you can do then is use your sine function to help you graph your cosecant function. And once that graph is drawn, then you can come in and either erase or just simply ignore your sine function. And so we have a graph of our cosecant function. Now, what would we say about the period for this cosecant function? The period is still going to be 2 pi. All right, so we have a complete cycle of the graph drawn on the screen. If we were to continue out to the right further, we would have another open up parabola here. So that would be a repeat of what we started with. And so we need, in order to have a complete cycle, we need one parabola opening up and one parabola opening down. And it takes a distance of 2 pi in order to see that happen. Okay, so let's move on to our secant graph. Now, it works almost identically, except that we're looking at the cosine graph. All right, so we're going to use our cosine graph to help us do the secant function. All right, so this one also should have asymptotes. So we need to first place those asymptotes. So we remember that our secant is going to be the reciprocal of the cosine. And so our asymptotes would occur at places where the cosine is equal to 0, because if the cosine is equal to 0, we're going to have an undefined secant value. So where is cosine equal to 0? Well, it's equal to 0 at pi over 2, so I'm going to put an asymptote here. It's also equal to 0 at 3 pi over 2, so I'm going to put an asymptote here. Now, on this graph, because it is best to see complete parabolas, I'm actually going to extend my graph back just a little bit and put one more tick mark, which would be negative pi over 2. I'm going to take my cosine graph and go ahead and extend it down. And then you can see that you would have had an asymptote here as well on your secant graph. All right, so let's draw our secant graph. Now again, we're going to use this parabola that opens down and this parabola that opens up. And we're essentially going to ignore what's happening over here for a minute. All right, so this parabola that opens down, when we do our reciprocal, it's going to flip up. And so we're going to have a parabola that opens up. It's going to share the same point, just like it did on the other function. And that will be part of our secant graph. Similarly here, we've got this parabola that's going to open up. When we go to our secant, it's going to open down and it's going to share that same point here. All right, and so again, once you have your secant graph drawn, then you can go in and you can either erase or just ignore your cosine graph. All right, so now we have a graph for our secant. And if you were asked for the period for your secant graph, you would also say 2 pi. Now this one is sometimes harder for students to see because part of your graph is on the positive x-axis and part of it is on the negative. So here's how to look at it. If you look at the distance from 0 to the end of the graph, you've covered a distance of 3 pi over 2. If you look at the distance from 0 back this way, this is a distance of pi over 2. It's not negative because we're talking about distance. Put those two together and we have 4 pi over 2, which reduces to 2 pi. So it takes a total distance of 2 pi to get one up and one down parabola. There is no amplitude for this graph, nor is there an amplitude for the cosecant one that we did just a minute ago, because the graph increases and decreases without bound. So we simply discuss the period and not the amplitude. Okay, so lastly, let's look at our cotangent function. Now, our cotangent function is similar to our tangent function, at least in terms of the fact that it has asymptotes and the fact that the shape of the graph is kind of in that S shape. So the first question, again, is where are your asymptotes? And so we're going to use our identity that says that cotangent is cosine over sine. And so we're going to have asymptotes wherever sine is equal to 0. And remember that your sine function was equal to 0, at pi, and at 2 pi, and continuing with that pattern. So we would expect to have asymptotes at 0, pi, and 2 pi. Okay, so let's draw this graph. I'm going to mark off the 5 key points that we've been using. 0, pi over 2, pi, 3 pi over 2, and 2 pi. I'm going to mark my asymptotes at 0, pi, and 2 pi. And again, we know that the graph has this sort of S shape, and I'm going to pop the calculator back up for a second so you can see what the graph actually looks like. Okay, so here's our cotangent graph, and you can see the asymptotes lining up just like we have marked off on our paper. And you can see that the shape of the graph is an inverse of the cotangent. Remember that your cotangent graph came in from the bottom left and hooked up to the top right. Your cotangent is going to do the reverse of that. It's going to come in from the top left and go down to the bottom right. All right, and so with that in mind, we can come to our graph and we can draw that graph coming through the 0 and coming down. All right, and again, we're drawing, when we draw those two pieces, we've drawn 2 complete cycles of the graph. And so what is the period for the cotangent graph? If we start at 0 and we end at pi, we have 1 complete cycle. And so the period of that graph would be pi.